How big do my ports need to be, and do I need oversized valves? Let's talk about it. All right, so we had a question about valve sizing and port sizing, and people sort of asking, how do they know what size it needs to be? Obviously, we've got to look at our minimal cross-sectional area and a couple other things, but they're talking about ratios of growth and stuff like that. And my response was, we've got to look at the whole primary induction length. And it just so happens we're doing this S3 Audi cylinder head at the moment, which I thought would be a great opportunity to show you what we're doing in Einstein motors with mapping the induction system. So again, we want to treat the primary induction length as a whole, as one unit. The head is not separate from the intake. It works harmoniously as one. So one is going to influence the other, meaning that if we've got a big port, we're going to need a small runner. And I don't mean smaller than the port. I mean not as much taper, not as much growth, to try and compensate to get the average velocity and inertia across that induction system close to our targets, and vice versa. If we've got a really, really small port, we're going to need far more taper in the runner to compensate for the small cylinder head. Again, it's about the averages, and that's what we've got to work with. So I thought we'd do a quick little one, because in the Einstein app for the 2J porting series, we've done a little extended section where we use the app and actually map the CSAs of the port. And by doing this, you know straight away what areas need attention, what areas don't. So we've seen with the 2J window was small, but just inside the window had a massive amount of cross-sectional area. That's because they don't develop the divider as well as some of the modern heads you'll see, like RB. Well, RB were ahead of their time, but this Audi is a great example, and I'll show you that now. So you can see in that port that they're using a raised floor and everything to eat up that cross-sectional area. So the transition from the common port to the two ports is far more seamless. The cross-sectional area variation between here and here is almost identical. And that's what you'll see in most modern cylinder heads. And this is really, really important, because again, it's about port energy. So if this part of the port's dead and this part of the port's fast, then it's going to pull our averages down. But if this part is fast and this part is fast, now we've got a lot of port energy. Now our average velocity across that port is much, much higher. That port is far more efficient and will fill the engine and make horsepower and everything, right? It's all about how much energy we have in that port and how efficient the port is. So if we've got low velocity costs us horsepower, so we don't want that. This is where the Audi head does the transition really well, as you've seen in the photos there. So today we've just done some basic measurements on this induction system, and now we're actually going to get into the Einstein app and just calculate the areas and map this induction system and see where it is. See what the MCA, minimal cross-sectional area, is and where. See how close it is to our RPM targets. I think our targets on this one are 8.8, so nearly 9,000 RPM, and I think 800 horsepower targets. This is deleting the DFI, the direct injector, and it's only going to run port injector. So that will change a couple of things that we need to look at. The manifold I'll also break down. And again, I'm not mentioning any names, but just because it's billet and shiny doesn't mean it's always right. And the measurements might even tell us that. So let's get into it. So what we've done here is basically just labeled the induction from the bell A, B, C, D, E, F, G, H at the valve seat. And we've given ourselves rough measurements so that we can calculate the area, or the CSA, of the total induction system. So now we can see where our points of improvement need to be and our points of letdown or poor design. So we're going to map the intake and cylinder head. So we're going to go into the Einstein app now. You'll see on the board we have A at 68. So that's the very, very end of the bell. We want to know what the airspeed is at that as well. Then we're going to measure B. B is actually the throat diameter in the, or not throat, or I should say the manifold diameter from where the taper starts. So the end of the radius to where the taper starts. This is pretty much just past this point is our actual induction length. And this is the problem with huge radiuses, is they only shrink the length of the, the relative length of the induction system. And we're washing out a lot of that signal. I got up to about an inch radius gauge and it was still bigger than an inch. So this has a massive radius on it, far too big, in my opinion, to do anything other than look pretty. C is also a tight spot. We're going to measure that up. That's in a stadium, so we're going to use the app in the stadium. D is also a stadium, which is basically a rectangle with two radius ends. So I have a stadium input in the calculator, which makes it really, really easy. And E is also a stadium, pretty much. We've got a little lump in there, so we're going to subtract a little bit off that. F is pretty much a diameter. It's pretty much round from there. G is round and H is the throat, and it's also round. So we're just going to go into the app now and add all them up and get some sizes on the board. All right, so we're in the Einstein app. We're going to go to the gold calculators. Flick through here. Now we're looking for, we're just going to use the CSA window app, which will calculate, here we go, which will calculate areas for what we're after. So we can do circle, stadium in this one, rectangle, oval. So the diameter for the first one is 68.25. Calculate, that gives us 3658. We'll just round it down. It's close enough. The next one is, and I'll write this on the board as I go, 50, which will give us about 1900. Yeah, 1964, that'll do, 1964. All right, now we're going to go to stadium. And our width for the stadium is 48.60. And 25.75, and calculate. That gives us 1109 millimeters squared. The next, so that was the pinch in the manifold by the looks of it, point C. So now we're going to do D, which is the manifold entry and the port entry, which they're pretty close. So I'm just going to treat them as one measurement, and that's 4950 by 2885. Calculate 12. So you can see we have a little bit of a problem already because we have a pinch in the manifold. So it's not tapered to the window like most intakes. Okay, 1249 millimeters squared. Okay, E, we're going to pretty much do the same. It's pretty, oh yeah, so we're going to go 50. And E is probably not exact. I'm using rough numbers here. because of the floor lump. So, and we're 12, 37, 44, yep, close enough, millimeters squared. So now we're going to do the circles again, and we're going to obviously have to times these by 2 because there's 2 ports. So we'll go back to circle. The diameter is 28.6 on both of those. Calculate. All right, so 642. So that's 1284. 1284 millimeters. Well, it's actually 85. 1285 millimeters squared. The next one's 1285 millimeters squared. And then the last one is a 30 throat. So 6, yeah. 1284, yep, done. All right, so let's go back. Sorry, I was just checking I got the last one right, calculating it in my head. 706.8. So yeah, that's going to round up to 7. So 7, so that's 13 millimeters squared. All right, so while we're in here, let's convert that to CSA for the imperial guys. So you could do it in this app by putting imperial sizes, but I didn't. So we're just going to go to the bronze free app and go into the calculators in the conversions, which engine conversion 1, I'm pretty sure it's in. And we're just going to go down to square inches and millimeters. So our first one is 3658 equals 5.6. Yeah, so I'll just go here. 5.67 square inches. Next one. Sorry, this is tedious, guys. 964 gives us 30044 square inches. Now 1109. That gives us 1.719 and 1249 equals 1.36 square inches. And 1237, 1.917 square inches. All right, we'll keep going, get this finished. 28, nearly there, guys, nearly there. All right, and the last one is 1413. 2.190. All right, guys, so we've got our sizes and we can see some problems straight away. The manifold actually has a tight spot in it right about here. That was our 1100 square millimeters. So it actually tapers down in the manifold, then pinches up to, or comes back up to the manifold window. So from here, we really need to work out what our minimal cross-sectional area is. I've had a quick look at the manifold. Obviously, this radius at 5.67 inches is massive, way too big for this this engine. Now, I've done a lot of this sort of stuff with 6 cylinders and 4 cylinders, and you know, you look at guys like Plasma Man, and they seem to be on the math fairly closely, and even radius size. We're under 1/2 inch on them now. So, and on a good induction, so a nice tapered runner at about that 2 to 3 degrees, we're finishing our diameter at about 17, 18, 1900 square millimeters. I'm not going to give you exact numbers because they're not my numbers to give, but if this was extended and had a little radius there, we would see far better results out of this intake even before we do it. And before I even do any calculations, just by understanding the growth ratio and the runner length that we have. So we're going to measure that up now. I'm going to take some port lengths, induction lengths. We'll work out what our induction length should be for that 8800 RPM. And we'll work out what our minimal cross-sectional area needs to be optimal for this engine at the RPM targets we have. And this will give us a little idea of what we got to do. But really, really simply, even if you're doing something like this at home, and this is something we've gone through on the Einstein app, looking at the 2J and basically highlighting areas that we definitely don't touch because they're already too big. And this is what it's all about. The better balance you can get, and this head, Audi heads are very, very good. I've done quite a few Audi heads over the time. They're very well balanced as far as cross-sectional area goes. And they'll show you why they don't need bigger valves as well. Again, unless we're going to really open all this up, but you can see how consistent this port is. Under that. Very, very consistent in the cross-sectional areas. So the port energy in this thing from the get-go is very, very good. If you compare those figures that we put in the Einstein app to the 2J, they were absolutely horrible. But as you can see, our throat and bowl area and blend up to the divider is where we're going to really look at. It could do with a little bit more in the E area, the body of the before the but we'll have a look at that. And the window is pretty good. So if we could lift this figure up to the window figure and then have the taper, it'd be pretty good, but there's not enough material in it from what I've seen already. So I'll look a little bit closer. We'll see what we come up with. But first of all, we need some induction lengths, and we need to actually see how big this port is relative to the RPM and cubic capacity, because that'll tell us how close we are to the actual targets. Let's do it. All right, so we just got to do port length. So we're just going to use the solder. I find it the best way. Again, some people use string. I like this because I can form it to the port. Now, generally with two valves, you've got to do both sides of the guide because the bowls will be a little bit different and stuff. But with the twin cam stuff, the 4-valve stuff, especially with these low guide ones, you can pretty much just go in. So all I do is set it up on the bottom of the seat, and if you press it into the casting, it'll form itself, and then you can just bend it over like so, and then you've got the port shape. So we're going to do the roof and the floor. I've already done that now, so that's our roof length and our floor length. So we add those two together and then divide by 2, and that gives us our port length, which come up at 74 millimeters. Then we measured our manifold length. Now I've gone to the bell, even though this radius will actually make it look about a 1/2 inch shorter. I've gone from the face to the bell, and he's going to also put a 3mm spacer, an insulator in here. So that brings us up to about 226 plus our 3. So let's say 230 millimeters in total induction length. So let's do some math. All right, so we're in the Einstein app. We're going to do induction length. Let's see where this is at. Actually, we'll go to the new calculator page, because I've built an induction page, primary length induction page, which has quite a few good calculators on it. Conversion between square millimeters and inches, cubes, just for reference. CFM on demand, which is another good one. This is more driven to 2-valve. I'm going to do a 4-valve version as well, but average airspeed, this is another one. Port window, that's in here, so I could have used that in here, same thing. And this will also have in your rectangle, so you can put all your different corners in. So that comes in really, really handy, especially with any twin cams now, especially. Or so that's what I like to do with the ports, is use them as a rectangle or square shape, and then you can add the different corner radiuses, because the corner radiuses are always going to be different. And any of the good 2-valve cylinder heads now generally have bigger radiuses in the slow side corner, because it's dead area. So on opposite the fast side in the corner, that radius will be bigger, because we're trying to offset that a little bit. All right, throat area, we don't need to work that out. Average CSA. Yeah, so this one you can put all your points in. So everything we've added up there, we can put in. So we have, we've even got a center line length here. So yeah, let's do this quickly. So what have we got? 1, 2, 3, 4, 5, 6, 7, 8. So we're going to use 8 points of CSA, and we're going to use our conversion, which we had. So it's 5.67. Then we have 3.044. Then we have 1.719. Then we have 1.936. Then we have 1.917. Then we have 1.992. Then we have 1.992 again, and the final 2.190. And our center line length 5. Is that right? Did I calculate it right? Yeah, 5 point. That's not right. Times, you dickhead. Sorry, guys. Divided by 25.4 gives us 90. All right, 9.055. Any remainders? No, that's fine. All right, and calculate. So our average, and it's also given us our total port volume of 379. So let's write this on the board. So we have these figures. So we have our average at 2558 square inches, our port volume at 379.5. So we know the volume is a little bit low, even with that big radius. So generally we want as close to cylinder volume in our primary induction length as we can. So I like at least that 92 to 95% as a minimal. And yeah, this is a little bit low, but we might do a capacity calculation exactly, because we have the bore and stroke of this engine. And we need to do a minimal cross-sectional area calculation now to see where the minimal is relative to our 8200 target. So let's go and see that now. Here we go. Beautiful. Now this is airspeed factor at minimal cross-sectional area. That's not the one I want. Runner length, let's do that. 8200. Yeah, I can leave it on imperial, doesn't really matter. Closing, it's probably going to be close to that. We'll go calculate. Okay, 13.9 inches. So as you can see, we're quite short considering we're only at 9 inches. So we're definitely nowhere near the third harmonic. This is the other one. Duration at 50 is about 201 from memory. Planum CSA, the average is about 3. I won't use that big radius because that's really not a good indicator. So let's go RPM 8200, and we'll bring the air temp down to a standard 86 and calculate. So 16.5, so very little camshaft, and you can see that affects it. So we'll add some more camshaft. Yeah, not too bad. So 14 to 15 inches would be a good start in total induction length, but we don't have it. All right, so let's go to our minimal cross-sectional area calculator. I'm actually going to add this to that page as well. So it's a running page with everything on there that you can just go back and forth with, because that's the feedback I've had, that these don't keep your calculations. But if I've got them all on the one page, so I'm going to make a twin cam page, so a 2-valve and a 4-valve page with the calculators that you commonly use. So we're just going to go into MCA with velocity. Is this the one? Yep. So I have the sizes here. 83 mil bore. We have a 92.8 mil stroke. Maximum RPM of 82. Airspeed, we're going to choose 620. That's the most common base. You pretty much use 620 with any cylinder head you want and still get away with it. Gives us a minimal cross-sectional area of 1.821 or 1175 square millimeters. As you can see, code C in the manifold itself is only 1109. So let's up that to 660 and calculate. There you go. 1103 is 660. So it's a little quick, but at the same time, the bell is a little big. So there's a fair bit of compensation happening here. So realistically, you could improve this by opening up C to say 1200 and adjusting that entry, how I said, extend it, smaller radius, make the runner slightly longer, proficiency-wise, and a 1/2 inch radius, and this would be a much better thing. So port-wise, we're going to have to concentrate on G, F, and E. They're the areas we want to blend. There's not much we can do about the choke in the manifold. I've already measured it. It's actually quite thin there. I'm going to pull the sides out slightly, but the roof and the floor, I cannot touch it. It's really paper thin, and I don't want it cracking. So, all right, guys. So this is a great example of why I absolutely insist on porting to CSA. We know the whole story of this engine now. We know our velocity is too high in the manifold, but also it's too big at the entrance. So our averages are going to come out not too bad. And we also know where we need to port. So GFE from H, that's our massive transition. The rest of this flows really well. We can't do much with that. I might try and, if I can bump that up to 1150, drop the airspeed down to 645, we won't be too bad. But this tells you everything, and this is why I love this approach. I spent near a decade on the flow bench before I learnt this way, and it truly cut my time and understanding down tenfold. It was just so much easier. Before, I was just, excuse the French, pissing in the wind with a porter and just thinking, oh, let's tidy that up, let's do that. You got no idea unless we look at this. And this is what we're doing in the Einstein app, showing you how to use it. And it's what we've done with the 2J porting series. It highlights straight away where you need to focus. And this exactly does that for you. Shows you what areas we need to focus on. what areas we definitely aren't going to touch. And it also shows you how good Audi designs a port. And these are a higher tumble port anyway. As you can see, they don't have a lot of short turn. I might get some more photos of it as we go. But yeah, there we go, guys. All right, guys, so what do we know? We know velocity is too high at the MCA. We know that we only have 80% of cylinder volume, so that's a little bit short. We know our average is 2.558 and our volume, which relates to our WOTC. So we're a little bit short. The airspeed's a little bit too high, but also the velocity at the belt is way too low. I actually should have went through velocity targets. I might do that in another video with a different cylinder head and show you a different calculator. But this is key, and this is something that took me nearly a decade to work out, is porting by CSA. It is key. It shows you, it really just highlights where the port needs help, and that's key. Like, and the Audi stuff is really, really good. If you're part of the Einstein group and you've seen the data on the 2J, you would have seen how bad that is relative to the Audi. And this is a hyper tumble port, so they really like a lot of turbulence in the chamber, hence why they don't have a lot of short turn. But also their transition through the port is absolutely brilliant. So you can see the areas we need to focus on is this area here from the seat that transitions in, because that's a massive jump there. So we need to fix that, but the rest of it is really good. I'm going to try and pinch this out in the manifold because it's got a really, really tight spot in the manifold itself, just in where the injector is. I'm going to move the walls out just a little bit, but it's thin. I can't touch the floor or roof because it actually pinches down and pinches in a little bit. But we'll leave that, or we'll take it to 1150 and probably leave it that. That'll get us down to about that 645 maybe. But this is the area we need to work. So as you can see, if you understand the CSA and learn to do a little bit of math, it changes your whole approach at how you port. Now we're not going, oh, I'm going to need a big window, I need this, I need that. It's pointless. As the MCA is in the manifold, it's going to dictate. So that's acceleration, decel. All we need to do is fix how it decels into the chamber, and that's going to be our approach. We want a nice gentle transition. So this is far better through the divider than the 2J was. That was absolutely crazy. I think we've seen nearly 200 or 300 square millimeters difference from before the divider to after the divider, where these are much, much better. There's barely 10 or 15 or whatever in that. So that's all. All right, guys, time to port. Let's do it. So guys, you can see straight away it's got a bit of core shift. There's almost nothing there. And then we have about a 40,000, 1 millimeter, 40,000 step there. So we have a little bit of core shift in these ports. And we have a really, really big lip on the short side. We're just going to lay that to the seat and go through and clean this up. Yeah, quite a big transition from the seat ring, as you can see, to the casting. So we need to make this casting bigger to transition that 1280 to the 1400 or so square millimeters.
can see you definitely want to use calipers with these Audi heads especially. What we're trying to do is get these walls parallel to the seat and back. So if I come into the seat, that's roughly it, and push it in, you can see it tightens up about there and it only gets tighter. So if I set it at that, okay, we're just loose now, yep, and come back to the seat, you can see we've got about 1.5 mil, 60 thousandths tighter just up in there. So we need to address that. Again, it's about balancing this cross-sectional area. And don't go putting a real big bowl in these. They're not designed for a bowl the way these hyper tumble ports work. I'm just trying to balance that. I don't want it to go in too deep. So that is as deep as I want to go into the bowl. So I'm just trying to blend this, and then I'm going to lift that roof slightly around each side of the guide to make more area for the air to turn around the valve. Other than that, we don't want to pull too much out. But yeah, we've got to fix this. So you can see how tight this side is to that side. So that's nearly 80 thousandths. So you can see that falls straight through.